Thank you all for coming. Today I want to talk about floating point conversion and more specifically about printf. So when I say floating point conversion, I mean all kinds of possible floating point conversion problems that you might have. I mean the typical ones are that you parse a number into a machine internal floating point representation, or that you print a number from a machine internal floating point representation. But in general, you could have other problems as well. It's uncommon, but it's possible. And so I published a paper last year at the PLDI 2018 about generating the shortest round trip format. And I'll talk about that a little bit because it forms the basis of this work. And this year, I'm talking about printf specifically, and more precisely the %e and %f format modifiers. %e generates scientific format, and %f generates fixed format, where it actually prints the entire integer part of the number, and then as many digits after the dot as the user specifies, or the developer specifies. But some of the ideas behind this work are also applicable to parsing. Now, parsing is still the one big left open problem that I can't talk about this year, maybe next year, we'll see. So why is printf a problem? Why is this interesting? Why do you work on this? So printf is a library function that comes with every libc, and it's found its way into many other programming languages as well. And now let's look at the performance of that function. And I've plotted a performance profile here, which you can also find in the paper. So the x-axis is the set of all possible 64-bit floating point numbers. And I just take the 64-bit pattern and interpret that as an integer to get, an x position on this chart. And the y-axis is the conversion time in nanoseconds for a single conversion. So this implementation, which comes with MSVC on Microsoft, on Windows, if there are 4 graphs here, right? So you can specify the precision that you want. This is %e formatting. And so if you use low precision values, it sort of looks kind of reasonable, but sort of 1,000 nanoseconds still seems a little bit off. But then if you go to higher precision values, you see that the graph goes up super linearly. Something is odd here. So what's happening under the covers? Under the covers, this is using a big num implementation, and it's performing big multiplications. It's allocating memory and performing big multiplications. And that's a problem, right? That leads to this performance profile. Now, in most cases, if you print just a single number, printf is fine. Please keep using printf. But if you have to generate files that contain a lot of floating point numbers, or you have some logging where you log a bunch of floating point numbers, then the performance can really make a difference here. So examples are, if you're working with 3D or 2D graphics, there's the OPS file format, which contains decimal floating point numbers. There is the SVG file format, which contains a lot of floating point numbers. If you generate one of these formats, you have to be careful, because the performance profile means that you can get very, very bad performance on your writer, on your file format writer. All right. And even if that's not the case, I want to make a case for improving this, because it's a low-level library function. This shouldn't be slow. You shouldn't have surprises when you're using printf. But if you are using printf, and depending on the numbers that you input, right? If you input numbers that are close to 0, you're fine. But if you input numbers that are larger or smaller, then you suddenly see like a 10x performance cliff, and that's really an issue here. All right. So my talk consists of 2 parts. In the first part, I'm going to describe a generic floating point conversion algorithm which works for any problem and any basis that might be involved. And then I'm going to talk about what's special about my algorithm and how I implement printf. And then at the end, I'll show some performance results from the new algorithm. So I start with a floating point number, f, and I expect that this is represented as a pair of integers, the mantissa and the exponent. So if you have some format and it's not two integers, then you first have to convert it into integers. This is pretty straightforward, so I'm not going to go into details there. Now imagine that you print the exact value in the target base that you want. So you have a binary, you start with a binary number and you want to print it in base 10. So imagine you print it in base 10. The entire number, all of it, all the digits. Now the problem is, depending on the bases, you might end up with an infinite number of digits. So obviously that doesn't work. So you have to cut it off at some point. So let's cut it off here without limitation of generality. Now if you look at the part before the cutoff, that's just a bunch of digits. And you could think of that as an integer. Or, more precisely, we can move the point to the cutoff point. So we take the number, the original number, and we multiply it so that the dot moves to the end. And in order to do that, we need to know the position at which we do the cut. So this position I can be positive or negative, right, depending on whether it's before the dot or after the dot. And then the equation is very straightforward. We take the original number, we multiply it by the target base to the power of minus I, and then we take the floor function. Okay? Now if we reverse this equation, we get an inequality because the floor function doesn't have, you can't invert the floor function as this, but you get an inequality out. Instead, x times the target base to the power of I is less than or equal to f is less than or equal to x plus 1 times the target base to the power of I. And so we've converted our number. The only thing that's missing is we need to figure out whether x or x plus 1 is the right value that we need to print, and that's basically rounding. So we need to figure out rounding here, and I'll talk about that a little bit later. So this is basically all the math you need in order to describe the general algorithm for floating point conversion. As I said, we take the number, we parse it into the form where we have a mantissa and an exponent, both integers. Then we have to estimate I. Now, this depends on the output format that we want to generate. In some formats, the output format says what I is. So in %f, for example, the number, the precision is exactly I. In scientific format, that's not the case. Instead, we have to figure out sort of roughly where we need to make the cut. And we don't have to be precise. We only need to overestimate the correct position. And I'll go through an example so we can see how that works. Then we go through the formula, we do the computation. If we had an estimate in the first place, then it may be that the new number x has too many digits. So we count the digits of x and see, oh, there are a couple too many. We cut them off, and then we also adjust I. We need the adjusted value of I in order to do the rounding correctly. And then we're ready to generate output. Let's go through a really quick example. Let's take the number 0.3 in decimal and convert it to a 32-bit binary IEEE format number. Putting that into an integer form is really easy. This is 3 times 10 to the minus I. Now, how do we estimate I? The IEEE format has 24 bits of accuracy, but it's sort of scientific format. So we need to figure out where our first digit is. And the easy way to do that is to compute the binary logarithm of the number. Now, as I said, we don't have to be exact. We just need to sort of guess in the right ballpark. If we're off by a couple, that doesn't matter. So let's take I equals minus 30. That's fine. Then we compute x. We just plug in the numbers. And I'll print this as a binary number. Now, of course, if you have a computer, this may already be a binary number, so there's no conversion going on at this point. But we find out that it has too many digits. Surprise. We have 5 digits too many, so we adjust the exponent. Now, this is our output exponent. Minus 30 plus 5 is minus 25. There we go. The next question is, do we have to round up? In this case, we have to round up. And it's very easy to see. If you look at the digits that we cut off and treat that as a fixed point number, 0.10011, is that larger or smaller than 0.5? Well, 0.5 is 0.1 in binary, And yes, this is larger than 0.1, so we have to round up. So that's exactly what I did here. If you look at the end of the number, it ends with 1, 0 instead of 0, 1. Now we're ready to generate IEEE output. We just have to compute the right IEEE exponent. Now the exponent is stored in a biased fashion in the number, so we have to add 127. Additionally, we have to add 23 because the numbers we're working with are integers. The IEEE format assumes that you have it as a 1.x number, which is not an integer. So we have to add an additional 23 to move the dot back to the right position. And we're done. We just plug together these pieces, and we've got our number. All right. So this is a general algorithm. The only case it doesn't handle is shortest round trip. In order to handle that, there is an additional step between steps 3 and 4 here, which I described in my first paper. So if you want to know everything about it, then you should totally read the paper. So the difficult part here is computing x. Now, if you have a big num implementation, sure, you just plug it in and you're done. But that leads to the performance profile that we saw earlier. So what can we do here? And there are several problems that we need to solve. The first one is x can be very large, right? Our exponent depends on the input. That can be very large. But our cutoff point I depends on the output. That can also be, large in a different direction. And so we need two ideas for making this work. One short side trip. There are actually 4 cases that we need to consider here. The exponents can both be positive or negative, but 2 of the cases are actually not interesting. I'm not going to go into details, so trust me on this. We'll only look at the last case, and that's already difficult enough, but enough for this talk, I hope. So I rewrote this. So I is greater than 0, so minus I is less than 0. So this is actually a division. So we have 1 multiplication, 1 division. Now, our mantissa, we started with IEEE format, so the mantissa, the size of the mantissa is fixed. So for a 32-bit number is a 24-bit mantissa. So that's fine, but then the source base to the power of the exponent can be very large, and the target base to the power of the index can also be very large. How do we handle this? So the first idea, all right, before I show you the solution, people have been working on this for almost 50 years, and the current implementations look like what I showed you. Not just the Microsoft one, but every implementation. Linux, Mac, Windows, they're all similar. And so when I show you the solution, some of you will say, oh, that's obvious. But I really don't think so. People, very smart people have worked on this and have not come up with a comparable algorithm. All right, so this division here is a division in the target base. And a division by a power of the target base in the target base is a shift operation. Right? If the target base is 2, then obviously that's a shift in binary. But even if it's a 10, it's a shift operation. And what we do here is we compute a very large product, and then we do a shift. So we drop the last couple of digits of that product. So if we're going to drop those digits, why should we compute them in the first place? And so the idea here is we don't multiply by the source base to the power of e, but we only take the first couple of digits of that in the target base. And we take, basically that's what the division at the floor function do here. And this is the idea behind Ryu, which again I published last year. And the reason why it works is that the difference between, all right, is this actually correct? No, it's not. If you take k equals 0, it's obviously correct, but we want to use a larger value for k. We want k to be as large as possible. And I was unable to find a closed form solution for this, but I was able to find a search algorithm that gives me a good k. And it turns out our k is always very close to I. And in fact, it's so close that it's basically constant. The difference I minus k is basically constant. So this becomes basically a constant shift at the end. So unfortunately, so that works when you generate shortest round trip format, but it doesn't work for printf. Why not? Because we can end up with a lot of digits. If the user specified they want 10,000 digits after the dot, we have to generate 10,000 digits, and we have to generate the correct digits. So this is not enough to implement printf. What happens here in terms of numbers, the source base to the power of e can still be a large value, and while we can cut off a couple of digits, it's not enough to make this a small multiplication. Now we get to the second idea. This is the magic. Instead of cutting off only once, we cut off multiple segments. Now, just the math is very simple. It's the same equation as before, except at the end we add a modulo with the target base to the power of the segment length. Now it doesn't look like this helps. It seems like we're doing even more work. We do a large computation, and then we do even more work to do a division and get the last couple of digits. But what happens here is, because we only need the last couple of digits, we don't need to compute the first digits of these results. And mathematically, what we can do is we can move the modulo operator into the floor function. Now, there is a fraction in the floor function, so that's not completely straightforward. But what we do here is we move the modulo operator in, and we keep the segment length, but we also have to keep the shift divider, the shift distance here, and add that to that. Now, does this help us? It does help us. It turns out the shift distance is basically constant for a given floating point type. So for 64-bit floating point numbers, the shift distance is about 64. And the segment length is something that we can decide. We can say, well, let's make the result fit into a 32-bit machine integer. So this means we do a modulo with the second parameter is like a 96-bit value. And so the mantissa is 64-bit. We multiply it with a 96-bit value, and then we shift out the last 64 up to 64 bits. Now every operation is a small operation. We have to repeat it because we have multiple segments in our number, but it's actually pretty straightforward. And what we can do to make this fast is we can pre-compute these values for all combinations of e and I. Now, that's a table. It requires some space. It requires, a few kilobytes in our implementation. We know that there are ways to reduce the size because this is a very, there is a lot of math here. There is a lot of redundancy in the factors that we compute. And so there is quite a few things we can do to reduce the table size by not, duplicating the same numbers again and again. And we can also, so 96 is like an odd number. We probably have to round up to 128 bits anyway, and we can use the additional bits to also reduce the table size. And with that, we get to the results. So this is again the graph that I showed you earlier from MSVC. As I said, other implementations have similar patterns. Now the new implementation looks like this. And what you see here is not just a quantitative change. It's not just 5 times faster or 10 times faster. It's the difference between quadratic behavior and linear behavior. Now there is one thing which is a little bit weird here. So the yellow line, why isn't that straight across? It's I'm saying that the performance is linear in the precision value. So the yellow number should just be a straight line here, right? The blue number a straight line, the orange a straight orange line, a straight green line, a straight yellow line. Why is that not the case? So the reason for that is if you convert a binary number to a decimal number, you always get a finite number of digits, of non-zero digits after the dot. No matter what you do, it's always a finite number. The reason for that is that 10 is a multiple of 2. It doesn't work the other way, but it works if you start with binary and generate decimal. And so because we know that, and because the precision value is 1,000 here, we can stop when we see the first 0 segment and say, all right, the rest is all zeros. We're done. And memfill is really, really fast. So there's really no computations going on anymore. If you want 10,000 zeros, we can deliver those very quickly. And if you don't believe me, right, whatever I say in terms of performance numbers, Stefan Lavave from Microsoft has taken this code, has carefully improved it. He's actually improved the performance. He submitted changes upstream, which is very nice. And he also did his own benchmarking against the standard implementations on Windows. And he has come to the conclusion that the new algorithm is a lot better. And if you want to hear him gush about my algorithm, you should watch his talk, which is online, which he held at CPPCon this year. And what actually happens there is that he works on the Microsoft STL, and the new STL already ships with both implementations for Ryu and Ryu Printf. It doesn't implement Printf, but there is a new module in C++ 17 called carconf, which implements character conversion functionality, and all of the floating point conversion, except parsing, is based on Ryu and Ryu Printf. So it may already be on your computer. If you have STL installed, you may already have my code on your computer. So that's pretty cool, if I may say so. All right, the original code is here. You can use it if you want. You can look at it. You can try it out. You can also wait for the results to show up in your favorite libc implementation. It's probably only going to take a couple more decades for that to happen. And one last note, in my own interest, if you are a professor and you think that this could be part of a PhD thesis, I'm very interested in talking to you. All right, thank you very much. Questions?
So we have time for one question, I think, before you want to start setting up. No question? So you mentioned memory allocations earlier on.
Yes.
So how much of this performance improvement is due to reduced memory allocation?
How much of this performance improvement is due to reduced memory allocation? Quite a bit. The allocated memory should be linear in the exponent, and so it doesn't explain the superlinear part of the curve. So there's definitely some to that, but there's also definitely some because we allocate the memory to do an actual multiplication, large multiplication with big nums, and that solves the, we don't do that anymore in the new algorithm, and that solves the superlinear part.
Thank you. So let's thank the speaker again.
Thanks.